Hello everyone, this will be the second lecture on vehicle dynamics. As a reminder, we're still in the soft start for ME3313, so this is non-essential material that won't be on any kind of exam or homework, but you might find it interesting. The main thing is just make sure you're able to view the lectures and you're able to see things on Canvas. So as far as schedule goes, on Friday I will do the exam 2 review. And then Monday after spring break will be when exam 2 will be scheduled. I'll send more details out on that. What I'll do for it is make the PDF available on Canvas, and then you'll be able to download that, complete the exam on your own. I'll give some extra time for it just for scanning it and printing it off, scanning it, that kind of stuff. And then you'll submit it on Canvas like you would a normal homework. So I'll send more details out on that, but Friday of this week will be the review, and then Monday will be the exam. Okay, so where we left off was suspension. So I know we talked about this in a prior class, but I'll go over some of the basics here. So solid axle, you don't really see this a lot in performance applications anymore. You used to be like, I think old muscle cars had solid axles. A solid axle is pretty simple. It's just a big chunk of metal that connects the left and right tires or wheels together. If it's driven, there'll be a differential in here that'll split power to the left and right sides. If it's not driven, it's just a big chunk of metal that connects the left side and the right side. The obviously problem with this, but one of the things that happens with this is when you hit a bump with one tire, that's going to get transmitted through the axle to the other tire. So essentially, a bump on one side will upset it'll upset the left tire and it'll upset the right tire, or vice versa. So these are really sensitive to road conditions, especially like mid-turn. If you're going around a turn close to the limit and you hit a bump with one of the tires, inside or outside, then it disrupts the whole axle. And it's pretty easy to experience if you have a rear-wheel drive muscle car that has a solid axle. You feel this. You go around a turn close to the limit, you hit a bump, the back end slides out, and it's can a little scary. It can cause people to crash. And that's one of the reasons why the internet meme about Mustangs and running over people at car shows is actually, there's some truth to that. It's because Mustangs had solid axles until just a few years ago. I think 2015 was when they did the redesign on it. And they went away from a solid rear axle to an independent rear suspension. And having owned a couple of the solid axle Mustangs, they say, yeah, if you don't know what you're doing and you hit a bump near the limit on the rear axle, it can upset it, and the rear end of the car kicks out quite a bit. Roll centers on this are tricky because it depends on how you mount the car to it. So, often like on trucks, these will be mounted with leaf springs, and there's not a really good roll center because they're mushy. The leaf springs are mushy, so the roll center kind of moves around all over the place and isn't in a defined spot. As if if it was controlled by a 4-bar linkage or something, you could guarantee the position of the instant center within the stiffness of the links. With leaf springs, the whole thing's compliant, so who knows where the roll center is gonna end up being. With a pattern bar, something like this controls the motion of as this bumps up and down. It prevents side-to-side motion. So if you put a side load like going around a turn, this pattern bar prevents this whole axle from shifting left to right. If you don't have a pattern bar and you have leaf springs, then all that lateral load has to go through the leaf springs. They're not really suited for handling that load. That's one reason why you shouldn't road race pickup trucks, especially pickup trucks with leaf spring rear ends, because there's just not any good control laterally of the axle. There's good control up and down, which is what you want in a truck, but there's not good lateral control with leaf springs. So a pattern bar and leaf springs, they put these on some old muscle cars, and it's okay. There's a whole lot better solutions to it. But for performance-wise, there's not a lot of real advantages here. It's mainly, if you're making a whole lot of power, or in a truck you need a whole lot of torque, you can make these things really very, very strong. You see a lot of drag racing still. The Watt linkage is just an improved pattern bar. The pattern bar, the instant center for the pattern bar is going to be its attachment point to the chassis. This will swing in a circular arc here. So as the axle bumps up and down, it will move left and right a little bit. With the Watt linkage, as the axle bumps up and down, this is a near straight line mechanism. the version of the watt linkage, and that point will translate mostly straight up and down and won't move left and right until you get to extreme deflections. But it's a lot more complicated. You need two links that are connected to the frame, and you need a pivoting link that's connected to the solid axle. Trailing arm you don't see a lot. The instant center for the suspension would be at this point. So you're looking at the side of the car, there'd be a point at the side of the car that these would be rotating about. One problem with this is the wheels actually move forward and backward as they bump up and down. Cornering, that Y-force we talked about in the previous video, creates a huge moment about this point here that this arm has to be sized to resist, and then the chassis also has to be sized to resist that. For a long trailing arm, it can be a really huge moment. I mean, you're talking maybe tens of thousands of foot-pounds that needs to be resisted. So NASCAR still uses these just because of the rules. They use really long ones. The longer they are, the better they are in general, because the wheels don't move as forward and backward as much as they bump up and down. But that bending moment gets worse. And you could put some kind of a link on it, like pin a link here and then pin a link to the frame. Maybe that would help. But then you have to modify this joint here, and you start getting complicated. And at that point, why don't you do something better to start with? Dion, I mentioned a little bit in class earlier, but you just don't see these. It's a solid axle with the differential and half shafts frame mounted. Basically, you take this mass that would be the differential, and you connect it to the frame, and then you've got axles and half shafts that transmit power. And the only advantage of this is you get some of the weight off of the solid axle. That's called unsprung weight. There's the sprung weight, which is the weight that's on the springs of the suspension. And there's unsprung weight, which is like the wheels and tires and part of the drivetrain that isn't controlled by the springs and the dampers on the car. And you ideally want as little unsprung mass as possible, just because you can control the motion of the sprung mass with your springs and dampers. Sliding pillar you just don't see, for good reason. It's terrible. There's binding issues with this. When you side load this thing going around a turn, it's hard to keep this thing from binding up when wearing out. You have to keep it from rotating about this axis too. I guess in the front you want one of them just to allow it to steer, but in the rear, if you're using this, you wouldn't want it to rotate, so you either need to make it a prismatic joint, which has issues, or you need to do two sliding columns. And I've seen some attempts to do this, and they're usually bad. So it just doesn't make a lot of sense in really any application. There's just better solutions. The only advantage I can see to this is the instant center would be off here at infinity, so the suspension would translate up and down. But one issue with that is when this whole vehicle, when it goes around a turn, because the tires act like springs, the tires are going to squish, and the whole vehicle is actually going to roll to the outside, and you're going to end up getting positive camber in both tires, which is not what you want. So that's true for things like tractors as well that are all solid, and the tires are actually the suspension. When they go around a turn, they're going to lean to the outside, and the camber's bad, which is why you should probably not road race tractors. It's just not going to work. Swing arm. So swing arm, we just have a fixed pivoting arm about the frame. Instant center is going to be right there. Instant center is going to be right there. You could use that to find the roll center if you wanted to. Well, I mean, it's real easy, right? You go from, oh wow, actually it's going to be really bad. So you'd go from this tire to this tire, this tire to this tire. The roll center would be right there. That's not great. It's actually going to be really high. You're going to have a lot of jacking forces on that. I'll talk about in a second. Your instant center is very short. Actually, would it be from there? I have to think about this a little second. Yeah, no, that's right. So you don't see a lot of swing arms. Biggest problem, the instant center is right here. So this tire is bumping up and down against a really short moment arm here. So it's going to change an angle. It's going to camber a lot as it bumps up and down, and that provides all sorts of camber control issues going around turns. Yeah, you saw some old cars like Beetles and things like that use this, but it's pretty rare. 4-bar is pretty simple mechanically, a little more complicated than the other kinds of suspension, but it still falls in the realm of being a relatively simple suspension. But you can do a lot of fun things with it. So it's very common. It's common in race cars. You can do lots of really good things with it. It's really easy to package. You see it on the front end of some independent suspension pickup trucks. You see it on just normal type cars. You see it on race cars. It's a good all-around suspension. Probably the best all-around suspension. McPherson strut. So 4-bar, I should talk about instant centers on this. It's where draw a line from the upper and lower control arm wherever they intersect. That's the instant center. If they're parallel, like in this case, it's off at infinity and you don't get any camber as this thing bumps up and down. If you move this pivot around, you can change where the instant center is at, so you can put the instant center exactly where you need it, which is why this is nice, is because you do have that flexibility in putting the instant center for the suspension wherever you want, and that'll also change where the roll center is at too. McPherson strut is a linkage transformation of this, so if you replace this revolute joint with a prismatic joint, you get the McPherson strut. So this is sort of a crank slider type suspension, which is a variation of the 4-bar, and it has a lot of the same attributes as has the 4-bar suspension. So the biggest reason you'd want to use McPherson strut is packaging. Let me clear off some of my scribblings here. You have to package this mount here. You have to have a place to put that on your frame. And if you want to put a big V8 or some other big kind of engine in here, there's just not a lot of room for it in this, or you'd have to have really stubby short upper control arms, and that has all sorts of problems that you don't want to get into, which I'll get into a little bit later. But you need room to put your big honking V8. This gives you room to put your big honking V8. So Max Strut's good for packaging, especially on the front of a car that's got a big engine up front. You've got room. So you can also tune where the roll or the instant center is on this. It's going to be extend the lower control arm and then run a perpendicular from this prismatic joint, and that's going to be where extend this out. Extend that out and then run a perpendicular out from that, and that's going to be where the instant center is going to be. So so you can tune that by where your lower control arm's at. So yeah, you get the same tunability on instant centers. The only downside of this is you have to have a nice prismatic joint. You combine that with a shock absorber, which is going to be a prismatic joint anyway, and it's not that big of a deal. The only main issue is this component wears out over time. That's the strut. The difference between a strut and a shock absorber is a shock absorber is just a damper. It's just for controlling motion. A strut is actually part of the suspension mechanism. So it's a little more beefy, a little more sophisticated component, and more expensive when you have to replace it. Okay, so I mainly want to talk about the 4-bar short long arm suspension. It's sort of the best all-around suspension, and if you can package it, it's going to be the best. So you see this in race cars, you see it in off-road vehicles, you see it on passenger cars. It's pretty common, and it's about the best mechanical suspension you can make. So why specifically? It's the ability to make it do whatever you need. So you can make it all parallel. You can make it so there's no camber gain. So it'd be great for off-road where you have lots of travel and you don't want crazy camber gain as the wheels bump up and down. For something like a race car, where we talked about how camber can make a little bit of a difference in the amount of lateral force your tires can make. If the tires are cambered in a little bit into a turn, they might make a little bit more Y force, a little bit higher coefficient of friction. And that makes your race car a little faster. So if you can position your suspension instant centers to where when the vehicle goes around a turn, the tires tip into the turn a little bit, you can make the car a little bit faster. So, and certainly if you can prevent them from leaning out of the turn, it's gonna help a lot. It might be a few percent, 5-10% more, but that's pretty significant at the end of the day. So we can tune this by moving these links around. What's going to be important are going to be the instant center locations. So you take the upper and lower control arms, find those intersection points for each side. That's going to give you the instant center. So the instant center for the right suspension would be here. Instant center for the left suspension would be here. So what we're going to do now is we're going to approximate the behavior of the suspension as if it was a swing arm. So we're going to say the left suspension is swinging about this instant center. We're going to say the right suspension is swinging about that instant center. And then we're going to find the instant center of the chassis with respect to the ground using that assumption. So to do that, we're going to assume that the tires are pinned to the ground at their contact point, and then we're going to run a link from the tire's contact point to the left instant center, from the left instant center along the chassis to the right instant center, and then from the right instant center back down to the ground over here. And that forms a 4-bar mechanism. This is called a virtual link, because there's not really a link there. There's just a sort of a virtual link at this instant. This works under these assumptions. The chassis is a real link, or it's a solid body, and then we have this virtual link from the instant center of the right suspension down to the ground, and it forms this 4-bar, which would have 1 degree of freedom like all 4 bars. And what this is going to give us is under the set of assumptions, we have the center of mass of the chassis, we have the roll center, which would be the instant center of the chassis with respect to the ground for this. This would be the instant center of the chassis with respect to the ground link, would be at this point where these links intersect. We call that the roll center, and that is, under these assumptions, the point about which the chassis will roll when you go around a turn. So when you take a car around a turn like this, there's going to be, so if we're turning the car to the right, the center of mass wants to go straight. So the effect of it is there's going to be an inertial force that's going to try to, inertial moment that's going to try to force the car to the outside. It's going to try to make this car roll to the outside. And so the difference between, so this would be, essentially be mass times AY would be the magnitude of that. So, or mass times V squared over R would be the magnitude, and it would face to the outside. So we're going to have this force times this moment arm here, and that's what's going to cause the chassis to roll to the outside. So if the center of mass is on top of the roll center, then there's no moment, and the car's not going to roll when you go around a turn. If the center of mass is really far away from the roll center, for the same value of this m times v squared over r, you're going to get more moment, and the car's going to want to roll more, and you'll need stiffer springs to resist that roll. So you might ask, why don't we just put the center of mass right on top of the roll center and our car doesn't roll at all when we go around a turn? There's reasons for that I'll get into in a second. So I'll make sure I've covered all my points here. So instant center is pretty easy to find. It's just the instant center for the 4-bar for the left and right. Roll center is the instant center of the chassis with respect to the ground. I haven't talked about this assumption, which is a bad assumption, turns out. We're assuming that the contact of the tire and the ground is a revolute joint. That's a bad assumption. Tires can scrub. So what that means is when your car bumps up and down, the tires actually are going to scrub in and out a little bit. So that's not actually a revolute joint there, and that's one of the pitfalls of the roll center method, or relying on roll centers, is it's not, in an ideal geometric sense, it is the point that the chassis rolls about, but the tires can scrub in and out, so it doesn't really roll about that point. So it's actually a little more actually a lot more complicated than this. But it's a good first pass for understanding the motion of the roll of a vehicle. So a couple things from a design perspective. So when the chassis bumps up and down, when you like hit bumps or you have aerodynamic loads or things like that, this roll center is going to move because these links are going to pivot, the instant centers are going to move, the roll center is going to move. So some rules of thumb for design is as the chassis bumps up and down, you want to preserve this distance, the distance between the center of mass and the roll center. You want this to be fixed as it bumps up and down. Why? Because if that distance changes, then the effective moment from that mv squared over r force, the moment from that's going to change if that distance changes. So what that would mean is, as you're going around a turn or as you're bumping up and down, how much your car's going to want to roll is going to change, and it's going to be weird for the driver. It might lead to some strange behavior. In general, you want things to be nice and consistent. The more consistent something's going to be, the faster or more control the driver's going to have. So you want that distance, that moment arm, to stay the same. You also don't want it to move a lot left and right. So when the car goes around a turn and rolls, this point's going to migrate around up and down, but it's also going to migrate left and right. This causes some very strange behavior. So I've done a lot of these designs for like Formula SAE cars, and if you just start putting points on there and simulating it, you can get roll centers that start out nice and well behaved and bump up and down with the chassis, but as soon as you start going around turns, these things will migrate 1,000 inches to the left or right, or do something really strange, or go off to infinity even. So that causes very strange behavior in the car. If the roll center is moving around left and right a lot, that's changing the effective point of rotation of the chassis. So if it's here, then your car is rotating about this point, and that makes sense. If your car is rotating about some point over here, that means when you're going around a turn, the car is going to be jacking up in the air or into the ground a lot. It's going to feel very strange if that's moving around all over the place. So the general rule of thumb I've heard on this, and I buy it, it makes sense to me, is to keep this roll center somewhere in a box that's about the size of your fist. So as it bumps up and down with respect to the chassis, you want that to be somewhere in a box about the size of your fist. So that would be about 2 or 3 inches of lateral migration would be acceptable, and then you want it to bump up and down with respect to the chassis within that same window. So imagine take this distance from wherever it is statically, draw a box or even a circle. It's about 2-inch diameter around that. And as this bumps up and down, you want the roll center to stay in that box, and you should be good to go. This can be above or below the ground. You can see roll centers above and below the ground depending on where the control arms are. Usually it's above the ground. There's no real problem with it being below the ground. The main thing is you really don't want it to cross the ground plane as the suspension goes through its range of motion. And I'll talk about why in a second. It's not a huge thing, but it can cause a change in behavior that might be upsetting to a driver. So you really want it to stay above or below ground in general. So why jacking? So jacking is something that I had a hard time understanding for a long time until I started really trying to just reduce it down to a basic 4-bar mechanism and how it would behave in a vehicle. I mean, I've seen lots of really bad explanations for this, so I'll try to explain this in a way that makes sense to people. So imagine your roll centers here above ground. So that's the point your chassis is rolling about. These pin joints here aren't really pin joints. They're where the tires are contacting the ground. And we've already talked about when a car is going around a turn, the outside is going to be doing more than the inside. Since the outside is doing more than the inside, that means there's more force on one side than the other side, which means there's a net force. Right? This is bigger than this, so there's a net force. And that net force is going to go to push those 2 points together. It's going to push the tires together. So if you push these points together, if you look at what this 4-bar is going to do, right? So if you imagine this is like a pair of scissors and we push the scissors ends together, then that's going to close this distance between these links, and it's going to push this point up. It's going to lift that point up. And so the scissors analogies is the best I can do, where your scissors are going to go from here to the pivot here and here to the pivot here, and when you close these scissors, it's going to lift this point up. It's going to try to lift the frame up as you go around a turn, and that's jacking. It jacks the car up as you go around a turn. And it's the delta between the left and right forces that causes it to jack. So if the roll center was exactly on the ground, then it would be very resistant to jacking, because this force would be like trying to push the ends of scissors that are fully open apart. You don't have a lot of moment there to cause it to close. Whereas when the roll center's here, you've got quite a lot of moment, right? You've got this moment arm here. If the roll center is way up here, then you've got a huge moment, and the car's going to want to jack really badly. And if the roll center is way up here somewhere goofy, the moment's even bigger. But at the same time, the moment's bigger, but as you push these in and out, this is going to move up and down less. So because it's I guess we say so here it's real resistant. Way up here, it's not resistant, but the effect is going to be relatively low. So there's some range in here where jacking's going to be a problem. So where there's lots of moment, and changes in the angle are going to have a huge change in the up and down motion of or we'll have small changes in the angle here. We'll have large changes in the height of this point here. So there's sort of a no-go range somewhere in the middle here where you don't want to be. Now you wouldn't want roll centers up here anyway. So essentially what that's going to do is it's going to rule out a zone here where you don't. Oh, my drawing's getting terrible here. Let me erase everything. There's going to be some zone where you just don't want the roll center to be. So it pretty well needs to be somewhere below the center of the center mass of the chassis and above the ground. Is sort of the box where you want it. I mean, you could put the roll center above the chassis. It's going to do weird things when you go around a turn. If you do that, the car is going to want to roll inside of a turn, roll to the inside of a turn, and it's going to have bad jacking forces. So you just don't really see that. I mean, it might be clever to do a car that rolls into the turn, but you'd have to deal with the jacking forces from it. It's pretty rare to see that. So usually you see this a few inches to below the center of mass, or a few inches of. Well, actually, it's it's actually closer to the ground than it is to the center of mass in general. So usually this thing is somewhere between the center of mass and the ground. Like on a Formula car, it's usually a couple inches above the ground. The center of mass is like 8 to 10 inches above the ground. So And then as the car bumps up and down, you want to stay above the ground. So on a passenger car where your center of gravity is going to be higher than that and your suspension travel is going to be more, you'd probably see this more, I don't know, 6 to 8 inches above the ground, something like that. So if this is below ground, so if the roll center is below ground, then you can see that as these forces act, it's not gonna jack. It's gonna push this point down as the scissors close, as the tires push in towards each other. It's gonna push this point down. And I don't know what that's called, but it's not jacking. It's the opposite of jacking. And so that's going to push the car down. So as the car goes around a turn, it's going to actually squat down to the ground. And the same things apply. As this moves further down, it's going to get worse, and at some point in time, it's going to stop getting worse because there's just, as these things move in and out, there's just not a lot of up and down motion at that point. But by then, your roll center is so far away from your CG that bad things are happening anyway. So there's some zone around here where you want the roll center to be. From depending on what kind of car you're doing, like a Formula type car, Formula SAE car maybe, you want to be 2 or 3 inches above or below ground. For a street car, make that bigger, right? Maybe somewhere 8 to 10 inches, 6 to 10 inches above or below ground. More common above ground. I haven't studied a lot of below ground, but it's not going to cause any huge problems from a jacking perspective either way. The main thing is if it changes from being above or below ground, then you go from lifting the chassis to depressing the chassis in a turn, and it might be weird if it changes. So wherever it starts, like if it starts here, you want to keep it from passing below ground. If it starts here, you want to keep it from passing above ground. Those are the general rules on roll center placement, and then you don't want it to migrate left and right. So how do you do this? You model it a lot. So, and it's really pretty easy to model in, the modern era of CAD. It's really easy to make a parametric CAD sketch. So here's a sketch I made in NX, a nice parametric CAD sketch. I've got my chassis. Chassis. I've got my control arms. I've got my uprights. I've got my tires here that have a little bit of base camber that's adjustable. I've created some extension lines here that are reference lines that give me, so this would be the instant center for the left, instant center for the right. It's going to give me my roll center placement here, and I can just sit here and bump this thing up and down, roll it left and right. This is an example I made for, this would be like a full-size car that I was bored in my office one day and decided to design suspension for a full-size car. And it's pretty good, I have to say. So this would be the base ride height of 8 inches. This would be from 0 to 3 degrees of roll. This is the roll center height, so it's about 6.8 inches off the ground. For 3 degrees of roll, it moves 1.8 inches laterally, which is within that fist rule. Camber starts at negative half a degree, and at 3 degrees of roll, it doesn't go to the outside. And then this will be the left. So the outside tire would tip more into the turn. The inside tire would not tip out of the turn, which is what you want. So you really want this tire to be at the right amount of camber. So the camber control is good, the roll center migration is good. When I bump the chassis down 2 inches, you'll see that this changes by somewhere around 2 inches. It's a little more than that, but still, we're still within the fist rule here, so it's fine. So bump and roll. Our roll center only migrates 2 inches, so we're good on that. Our camber control is good. All of our tires are tipped the right way. 10 inches, so this would be when the chassis is lifted up off the ground and roll. Again, roll center migration is good, camber control is good. So again, how do you do this? First off, you need a model. So you can make a generic model like this in a CAD sketch, and then you move points around. It's usually easiest to move these points around. These ones have to fit inside your wheel, which is interesting, but these points here, you have to move those around, and you have a lot of freedom at these points, usually these upper points, but you know, this point and this point really change things a lot when you move them around. So there's other things that are impacted by this too that I don't really have the time to go into in this video. So it's always going to be a compromise of your roll center and camber gain, and the other things like caster, and this will be kingpin inclination, and a whole lot of other complicated things that I could go into a whole other video on. But it's always going to be some kind of a compromise. But in general, you sort of want to start with getting your roll centers to behave, getting your camber to behave, and if you do that, and you don't do anything too weird with these points, if there's not too much inclination on this axis, things will behave fairly well, at least to get started with. So this is that information plotted. So this is roll center height. So through roll, so this is roll down here, roll, and then this is roll center height. So you can see it doesn't change very much at all with roll. Lateral motion versus roll. So this is roll, this is lateral motion at the different rides. So you can see this is nice and linear. It doesn't do anything weird. It doesn't migrate that much. Very well behaved roll center. So this would definitely be very acceptable for roll center behavior. All right, a couple other things. Some questions here. So kind of changing topics. So I did a little bit of simulation modeling, and one of the things that comes a lot, especially with things like Formula SAE teams or vehicle teams, performance teams like solar car, any kind of vehicle that you try to want to make it perform better. So what variables do you change if you want to make something better? So I did a little work in a simulation model and changed some of these parameters and plotted some results. So essentially, the question here is, if you could pick one of these variables and make it 10% better, which one would you pick? So if you're going to pick one of these things to change to make your vehicle go faster in a straight line, what would it be? So it's the wheelbase, it's the balance, where the center of mass is forward to backward, the mass of the car, the CG height, downforce, drag, gearing, the traction, coefficient of friction of the tires, or power. Which one of those things would you make better? So what I did is make each of these things 10% better, ran a simulation on it, and a pretty accurate simulation model that's got a really good tire model on it, and a tire that's had actual tire data from it. So these results are pretty trustworthy within the assumptions of the model. And what you'll find, and this is true in almost every simulation I've run, it's these things in straight line that matter a lot under a couple of assumptions. So mass, so this is a 75 meter acceleration time, which would be for something like Formula SAE. But you can see that most these things don't seem to have that big of an effect, and then these things have a huge effect. So decreasing mass, right, making everything lighter, that always makes things better in cars. And it gets back to that load sensitivity thing, but it also gets into, and the ratio of power to mass is going to affect how fast your vehicle is. So not only do you get more out of your tires, but you've got less mass to accelerate for the same amount of power, so you're going to be faster. This one's really interesting because changing gearing has a huge impact, and it's easy. All you do is change your ratio and your differential, or change your chain, your sprocket ratio if it's chain driven. It's the easy change, and it makes a huge difference. Now at some point, once you get the gearing right, it's not going to make any difference. But you know, for this model and just this set of parameters for the car, just a small change in gearing had a huge impact. And you'll find that in straight line acceleration, getting the gearing right is the most important thing you can do, and the simplest thing you can do. It's the cheapest thing. It doesn't add any weight. And if you've not bought components, you know, if you do the analysis ahead of time and you buy the right gear ratio at the start, it doesn't even cost anything other than some simulation time. Adding power obviously makes things faster, but adding power is expensive, right? So here we get the same benefit from just changing the gearing as adding 10% power. So making the gearing 10% better is basically the same as getting 10% more power. And again, at some point, you're going to get the gearing right, and then this effect goes away, whereas adding more power is always going to make it faster in general, up to the traction limits. So some of these other things that don't change, wheelbase, very subtle effect. Downforce at lower speeds, it's a very subtle effect. Adding traction, so here in this case we are not traction limited. If we were traction limited, so if we had enough power or enough gearing that we don't have enough traction, then all of a sudden this would be one of these significant factors too. So this is something you have to take not with a grain of salt, but in the model, the vehicle that was modeled, it was not traction limited. So for something that is traction limited, you would expect to see this to be a significant concern. So that's something that's not shown in this model that you need to pay a lot of attention to is traction. So as soon as you start to be traction limited, it's going to be one of these significant parameters. Add rear weight, pretty subtle change. Again, it's getting into the traction thing. So if you're traction limited, more rear weight might actually help because you're traction limited and you get more weight on the rear tire. So these you'd expect to see would be more important if you start to be traction limited. Lower CG, a little bit of a help. Decreased drag, a little bit of a help. Again, depends on how fast you're going. If you're talking about quarter mile, this is going to start to be a big thing at some point in time. So again, this is for one set of parameters for a vehicle. In general, you'll find that regardless of the vehicle, mass is always going to show up in this. Gearing is always going to show up until you get the gearing dialed in right. More power is always going to make you faster, assuming you have the traction to do it. At some point in time, adding traction is going to be the limiting factor. And then these other things are usually fairly subtle until you start getting to higher speed. But so in general, the things that are the easiest, not the easiest to do, but the things that will apply to any situation really, if you can decrease mass, it's always going to be better regardless of what your vehicle is going to be. If you can get the gearing optimized, regardless of what the vehicle is going to be, it's going to help. Adding power, there's going to be a limit to that. At some point in time, there's going to be a practical limit to how much power you can have, and it's going to get expensive. But these things are really important. This is going to be really important here, as we'll see in a second. So let's go around to corner now. So let's take this set of parameters. If you can make wheelbase, balance, mass, CG height, downforce, drag, gearing, traction, power. If you can make each of these things or one of these things 10% better to make a car go around a turn better, which one would you do? So if you could pick one of these things and make it 10% better to go around a turn better, what's gonna be the best one? So this is skid pad G's. So higher is going to be better on this. This is a 16.25 meter diameter skid pad, lateral acceleration in G's. This would be the baseline number. Wheelbase, very little impact. Changing anti-roll bar made it a little bit better. And in this case, I basically changed it one way and then changed it the other way and picked whichever one made it faster. So that was balancing the car a little bit better with the anti-roll bar, made it a little faster around the turn. Adding rear weight balanced the car a little bit better in this case and made it a little bit faster. Lowering the CG helps the tires out, makes the load more even, makes it a little bit faster. Widening the track made it a little bit faster. It evens out the load on the tire, so it gets rid of that load sensitivity. Adding downforce made a pretty significant impact on this. Decreasing mass made a huge jump going from here to here, just decreasing mass. Adding traction, way up there. That's what you'll find in cornering. The limiting factor in cornering is almost always the traction capability of the tires. Balance matters. These things all through here affect. So this is balance, balance, balance. So like balance and balance. This is tire sensitivity. This is downforce. Again, if you're going faster, the downforce is going to be more important. But traction is the limiting factor going around a turn. So because I guess the easiest way to explain that is for about any car, you can make it hit the traction limit going around a turn. You just go faster and you turn the wheel, and at some point in time you're going to hit the limit for any vehicle. Accelerating in a straight line, you have to have enough power to be at the traction limit. That's why it didn't show up here. For a more powerful vehicle, then all of a sudden you're going to see a similar result where traction is going to dominate. So in general, more traction is going to be better. So I guess if you could pick one thing, if you've already got a vehicle built and you can't change it, you can't make it lighter, and you wanted to make it faster in every way, better tires. That's the easiest thing to do. I mean, you put better tires on it, it's going to be significantly better in a straight line. Significantly better around a turn. In a straight line, better tires are only going to make you faster if you've got enough power to use that extra traction. From a design perspective, the best thing you can do is decrease mass. So for going around a turn, it's better. For accelerating, it's better. So from a design perspective, get the mass lower, and that's like the golden rule of racing, is make the car as light as possible. It's better. It's better in every way. I mean, it literally helps everything out. So there's for a properly balanced and set up car, lower weight is always better. There's no advantage for having more weight. No advantage I could possibly think of. And in fact, if you talk to any race car engineer or any judge at like a formula competition, it's always about the weight. The weight's the most important thing. Gearing matters too. That's a design decision. So for a straight line, obviously doesn't affect turning very much, but getting the gearing right has a huge impact in a straight line. So the most common, the biggest, most impactful design parameter between these is mass in both cases. So weight's king. Power obviously makes things faster in a straight line, but there's going to be a limit to what you can do with that. These other things are pretty subtle. These are mainly tuning. Once you have the car made, these are mainly tuning things here. But from the best thing you can do from a design perspective is make it light, get the gearing right, and put the stickiest tires on it you can, and those are going to have a much more significant impact. Outside of that, really something that's not modeled in this at all is the driver. Driver is going to be more important than almost all of these things at some point in time too. So the driver is incredibly important too. But as the engineer, you really can't control that. So. All right, so some just rules of thumb for making vehicles faster, lighter. If you make the car lighter, it's going to be better. Obviously, more power until the point where you're basically you keep adding power until you can spin the tires at the fastest speed in the longest straightaway, which at some point in time that's going to be an absurd amount of power. But more power, wider, stickier tires. So I haven't talked about wider tires at all. If you just look at the coefficient of friction model, there's not area in there, and why would making a tire wider make it have more friction? It does. You can see that from any tire model. You can see that in drag racing. It does. It doesn't actually change the area of the contact patch that much on the ground, so it's not actually the area of the contact patch. That's more of a function of the tire air pressure than it is the tire width. It changes the shape of the contact patch, and it has a really interesting, subtle effect on the amount of friction a tire puts out. So there's a lot of black magic and voodoo on tire size that I don't want to get into. I'm not actually that much of an expert in that area anyway. But wider, stickier tires. The stickier part, softer compound, makes a huge difference. You can see that here, huge difference. I mean, just for example on that, like the tires they use in Formula SAE, they have a coefficient of friction of like 1.3 or 1.4 on asphalt. High performance street tires might have a coefficient of friction just over 1. Really junky hard tires might have a coefficient of friction of like 0.8 or 9. So it makes a huge difference. 30% more coefficient of friction. It's nuts how much of a difference it makes. Fix the gearing. You want as much gear ratio as possible. So that's shorter, which means the numeric ratio is higher. So the driving gear is smaller, the driven gear is bigger. You want to go to the most extreme ratio you can that gives you the top speed you need for whatever you're trying to do. You want the gearing to be as short as possible, and it's going to make your vehicle faster. You're going to use your power better if you do that. Lower the CG. That helps pretty much everything. Makes the tires more evenly loaded. Move the CG towards the back if you can. That usually is a design parameter that you may or may not be able to affect. All-wheel drive's obviously going to be better than anything usually, but it's more complicated. It's more expensive. For a properly designed rear CG type vehicle, rear-wheel drive is really pretty good. Front-wheel drive doesn't make a lot of sense in really any kind of racing. Going around turns, accelerating, it just doesn't. It's dominated by rear-wheel drive and all-wheel drive. So this is going to be better, but this is really good if you do it right. This doesn't make a lot of sense in most kinds of racing. It's always some really bad compromise. Keep your roll centers well behaved, which don't let them migrate left and right. Keep them moving up and down with the chassis. Keep them close to the ground, but pick one side. Balancing a car I haven't talked about a lot, but it's always going to be better to balance a car by adding grip, not removing grip. So if you think about anti-roll bars, An anti-roll bar makes the front or the back of a car stiffer. So if you make the front or back of a car stiffer, you are transferring more weight, which means you're pushing one tire more into that nonlinear range, which means you're giving up total grip on that side. So tightening up an anti-roll bar makes the car worse on that side, and it makes the car overall worse by making one tire more heavily loaded than it would normally be. So you're actually reducing the overall ability of the vehicle to turn. So it's always better to balance the car by adding grip. So how do you do that? If you can, use a wider tire on the side that's sliding. Right? If your car's oversteering, put a wider tire in the back instead of punishing the front of the car for a car that's oversteering. Make the tires wider in the back. And at some point in time, you can't do that. Right? If you're in the middle of a race or something, you can't do that. But then that's where using anti-roll bars to fine-tune the balance comes into play, because it is a pretty subtle effect with them. Whereas changing tires is a not subtle effect. So you really want to balance something by adding grip, not removing it from a design perspective. Fine-tune balance with anti-roll bars. That's what they're really good at, is fine-tuning something once it's done. Make your tires as evenly loaded as possible, left, right, fore, aft. That matters a lot. I mean, it's a fairly subtle effect, but it matters. Once you got something designed, it matters. Control camber. Again, fairly subtle effect, but you want your tires tipped slightly into the turn, depending on tire construction, usually 1 to 3 degrees or so. Make tires as evenly loaded through bumps. That's shock absorbers. I haven't talked about at all, and I'm running out of time for this lecture. But with your shock absorbers, what you really want, just because tires are nonlinear, as we talked about, when they're going up and down on bumps and the normal force is changing, then you're going to have overall less friction capability if they're going up and down on bumps versus if the force was relatively constant. So you really want your spring and shock absorber to keep your tire normal force as constant as possible. And again, I haven't talked about this at all, so I'm saying this without justifying it at all. But you really want your single wheel spring rate. You want the spring rate for each tire to be very soft. Again, I don't have the time to talk about it in this video, but so that's why those have asterisks. So you just have to trust me on that one for now. But you want your tires to be evenly loaded through bumps, and you want the soft spring rate, which is part of keeping them evenly loaded. So if I have time later on, I might make a video talking about that, but I need to make a bunch of models for that too. I've already had the models for this skid pad and acceleration here. So anyway, in anti-roll bars for roll resistance, I haven't talked about either. So a few things on that again, we talked about everything else on this, but those are, we'll save for a later time. So all right, so that's it for this lecture. Again, for those of you in machine dynamics, this is, I don't want to say it's a throwaway lecture, because it's not. It's interesting stuff, but it's not required for the class. Some of you might not be interested in vehicles at all, but for everyone else, this would be helpful if you're on a design team and you wanted to make a vehicle faster. So again, for 3313, we'll do a review on Friday. We'll do the exam on Monday. So I'll communicate with you all via Canvas. So that's it for today. Thank you.